Hello, class. It's your teacher, Mr. Max, here with another lecture for you guys to go through. This time we're going to be talking about classifying the properties of matter. So last time we went through and defined all our different types. So we had elements, compounds, homogeneous mixtures, and heterogeneous mixtures. And now we're going to look at possibly some examples and then work through how we would classify each of them. So let's get started. We're going to start with which of the following of these are elements. So let's start by trying to remember our definition of an element. An element is the simplest the simplest substance which cannot be broken down further chemically. But how do we know if something's an element or not? So we have some examples. We're going to start with an atom. Before we get started, actually, let me explain this picture off to the right. If you have not seen this before, this is the periodic table. So every element we know is on this table. There are a bunch that are more common than others. These ones, especially over on this top right, seem to be used more for chemistry, in my experience, than these ones on the bottom. Some of these ones on the bottom even are man-made, whereas a lot of these ones on the top come naturally in the earth. So one great way, and I would say the best way, to know if something is an element or not is to see if it's on the periodic table. So let's start with our examples. So we have an atom. An atom is not an element. Actually, elements are made of atoms. So we also don't see it anywhere on the periodic table. Sodium. Sodium has an abbreviation for Na. So Na, we can look and find that it's number 11 here. So sodium is an element. Grass. Grass is, let's think about grass. What is it? It's kind of an annoying chore for us to have to cut. It's a big substance, a big material, especially compared to most elements. Most elements are very small, so it also does not show up on our nice table here, so that would not be an element. We also have boron. Boron has an abbreviation as B. So if you can try to find B over on our table, you would see it is number 5, boron. So boron is an element. We also have carbon. I think we mentioned carbon as an example in our last video, and we can see that carbon, which has an abbreviation of C, is right here as number 6, and then pizza. So pizza, again, like grass, is a very large thing relative to our elements. It is also not a pure substance. When you think of pizza, there's lots of different toppings and layers, and so it is not even in the same group of elements or pure substances. So can we find out if we do not know if something's an element or not? We search the periodic table. So that is the best way. Let's start talking about compounds now. So which of the following of these examples are going to be compounds? First, let's remember our definition. So a compound is a material that is made of 2 or more elements. So our picture off here to the right is one way to show a molecule. It's also a compound that is actually very complex. So since our definition is 2 or more, this picture might have around 20 different elements within it. But let's start looking at our examples. So aluminum is our first example. Aluminum's abbreviation is Al, and it is actually on the periodic table. So if we go backwards, I think we can find aluminum as number 13, right here. So that is actually an element. Carbon dioxide. So carbon, we learned just a few minutes ago, is an element. Now dioxide. The dioxide stands for 2. So di stands for 2, and oxide stands for oxygen. So CO2. Now that has 2 or more elements. It actually has 3 elements in it. So carbon dioxide is a compound. Sugar water. So let's think about sugar water. There are 2 things being joined together, but neither of them are elements. So sugar water actually is a mixture. It is not a compound. Sulfuric acid. This one might be difficult if you don't know. And if you're ever in a situation where you don't know, well, let me put it this way. If you're ever working on homework or a worksheet that I gave you, you can always look up what sulfuric acid looks like just by Googling sulfuric acid. Most of the time, though, I will make it very clear that it is a bunch of different elements joined together. So sulfuric acid has more than one element combining or joined together. So it is also a compound. Let's think about an orange. So when you open up an orange, we have the fruit and then all those different little, almost like barriers in between each layer on top of an outside peel or barrier as well. So there's lots of different things in an orange. I would say it is better described as a mixture. A pencil, also a much larger thing than a compound. Compounds are very small and need special equipment to see. Same with elements. So if something is big enough to see with the naked eye, it is usually a mixture. So a pencil is a great example of a mixture. Let's look at nitrogen. When we think about nitrogen, it has an abbreviation of N, and it is actually on the periodic table. If we flip back to the slide just before this, I believe it is number 7 on the periodic table. But really, how can we tell? I like to think if it is something that is hard to see, it's a pure substance, something that we can't see with our eyes, usually is a pure substance. And also, if there's multiple elements, that's the key, going back to our definition. If you see carbon and oxygen, if you see maybe oxygen and hydrogen, or anything else, if you have multiple elements there, it is a compound. So, yep, important thing, a group of elements. Now let's talk about homogeneous mixtures. So, let's again remember our definition. So our definition states that a homogeneous mixture is a mixture with uniform composition. So I love these pictures as examples because they all look the same. Every circle looks the same as another. This one, you can see that there's different sizes of circles, but if you look at a big circle, it has 6 circles around it, all in the same position all the way around. And same with this. This picture on the right, it has groups of circles, but the same amount of space in between each of the groups. So they're uniform. So let's start with our first example of salt and sand mixture. I would say that is a homogeneous mixture. A great example of a mixture, let's go back to the salt and sand. If the salt and sand mixture is very well mixed. So that's the key, is if something is very well mixed, that means it is uniform throughout. If this salt and sand mixture is maybe someone poured a layer of salt and then a layer of sand, or the other way around, and doesn't mix it ever, I would say it would be heterogeneous. So some of these examples can be confusing, or you may need more clarification, but if it ever says well mixed, that means it's a homogeneous mixture. We also can look at salt water. Salt water from the ocean is very well mixed. We can see that the water and salt are one, and the water kind of absorbs the salt. So I would say that is a homogeneous mixture. We also have purified water, which is a great example of a homogeneous mixture. A lot of the times, if it says pure or purified, it also means it is homogeneous. We have hydrogen. So hydrogen has an abbreviation of H and is actually the element with the number 1. It's the first one on our periodic table. We have air with dust in it. Air with dust in it would be a heterogeneous mixture, not a homogeneous mixture, because the dust would not be uniform across. You might have more dust on the top of the air or in the middle or on the bottom, but not evenly spread out. An apple is also not a homogeneous mixture because you have the core of the apple on the inside as well as a stem. So it is not uniform all the way through. Iron is a good example of another element. Iron's abbreviation is Fe, so it means that it is an element on our table. And then iron with rust. So if we're thinking about an iron beam with rust on top of it, the rust is on the outside, while the iron on the middle is the same. So since there is a layer in it, it would be not a homogeneous mixture. And then an orange, I think we talked about this one on the last slide, has a lot of different things in it and is not uniform. So the best way to think about it is if you can see inside, or maybe thinking of the mixture at almost a microscopic level, does everything look the same all the way through? And finally, we have a heterogeneous mixture. So looking back at our definition, it is a non-uniform mixture. Pizza is my favorite example because you can see that the olives are not perfectly distributed. It's just kind of thrown on there in any order. And we're going to go through these same examples a little bit quicker. So sand and salt mixture. If it is not mixed well, I would say heterogeneous mixture. If it is mixed well, I would say homogeneous. So we would need to ask some clarification. Salt water is homogeneous. We just said pure water is homogeneous. Hydrogen is an element. Air with dust is a great example of a heterogeneous mixture because it often will settle in layers. An apple, another great example of a heterogeneous mixture. For some reason, food works really well because we have our apple core and then the apple itself, which are different. Iron, we said, was an element. Iron with rust was a nice layering situation where we could see a heterogeneous mixture. And an orange is a great example of a heterogeneous mixture because we have our outer layer, our outer peel, and then we have the fruit and even a bunch of different barriers within the fruit. So how do we know? Again, it's if something is non-uniform. If something has layers is another great way to think if there is a heterogeneous mixture or a homogeneous mixture. So I hope this helps understanding how to classify different things. Please let me know if there was any confusion or if you have any questions. And I look forward to hearing from you guys.